use the parameter A and B, what we have used in the generalized example. This was a generalized transfer function we have taken. Then input is a step input. A and V values, we have assigned the values of A and B as 9. Then after assigning the values, we have got the roots. So this function, what we're talking about, the function had a poles at the origin that will come from the unit step. And then we had the two real poles that will come from the system that you know already. Then I have talked that input port at the origin will generate what? Sorry. Okay, see, you can see this input port, input pole, the input pole at the origin will generate what? It will generate a force response, whereas we have two real poles that will come from the system. System means, I told you, from the transfer function, that will generate an exponential natural response. So this I have talked yesterday. So let's move further. Then after that, when we are talking about this, that the input port at the input pole at the original will generate the constant force response, and each of the system poles on the real axis will generate what? Exponential natural response. And when it will generate the exponential natural response, whose exponential frequency will be equal to pole location, that I have already told. Whose exponential frequency will be equal to pole location. That's very important. So pole is whatever the location is of the pole, that is this location, 7.5. This is the location of the pole. So A is a time constant, 1 by A is the frequency. So its exponential frequency will be equal to that pole location. Then we can obtain the exponential frequency from that pole location. Hence, we can, without any tedious calculations of using the partial fractions and then using the inverse Laplace, we can simply write the output. Initially, we can write output can be approximately written as, so we can write output as C of t will be equal to K1 plus A1, whatever you want to write. This is a constant. E raised power minus first pole on the negative real axis is 854 into t plus K3. Second is minus 1.146t. So that's exactly the location of the pole. Minus you have to consider here. We don't have e raised by minus some. This is a minus. What are the location of the pole is? The same we have to write here. So this will be the initial output. So the response is, this response is what? This response is an overdamped response. Now we can see that pole, we can see that when we have located the pole, the poles will tell us the form of the response without any tedious, without any calculations of what? Without any calculations of partial fraction, without any calculations of inverse Laplace, we can still have an idea about the response. So it is very important. Now we can have a look here. See, number one, we have considered this number one case is the overdamped case here. This is overdamped case. I will encircle this. This is an overdamped case. You can see the pole zero plot. Pole is on the negative real axis. Second is also on the negative. These are system poles. And one pole is because of the step input that we have not shown it. That is on the origin. Now you can see if we are going to draw this response. So Laplace inverse of 1 by s is 1. And then for these two, we are writing it constant. I have not calculated. I will not calculate it. You can later, we will calculate in the numerical. So constant K1 e raised power minus constant K2 this. So here you can very clearly see that what are the constant values are there. One will be minus, one will be, I am not worried about that. So once you are drawing a graph of this, you can see the transient response is like this. It will start initially and then finally it will settle down at some value. So what is the physical significance? Physical significance here is overdamped refers to a large amount of energy absorption in the system. So if we talk about the overdamped system, it refers to what? Large energy absorption. Large energy absorption of the system. So this is an overdamped. Now that will restrict what? That will restrict the transient response from overshooting. See, if overshoot means transient response can go like this. One, we have a steady state value, let's say. It's settling down at this value. This is a response and this is a time. It is settling at this value. So this type of response will not allow the transient response to overshoot. That means it will not allow it to go over the steady state value. So it inhibit means it will restrict the transient response from overshooting and also from oscillating about the steady state value. So this type of response, you can see there is no oscillations, there is no overshooting. Once there's a transient response, it will settle down at value. So this response means actually there's a large energy absorption of the system. That is number one. Then number two, it will restrict what? It will, this type of system will restrict the transient response we are recording it or not? Yeah, I think we are recording. Okay, what we are talking. So this type of system will restrict the transient response from overshooting, and then also it will not allow it to oscillate. Overshooting and oscillating about the steady state value. So this is very important physical significance. So when we have this type of response where we have one pole from the origin, that will be that from that we will get a constant forced response, and then we have a two natural exponential response from the system poles. Then in that case, this type of system will restrict the transient response from overshooting, going above the steady state value, and also it will not allow it to oscillate about the steady state value for the step input, because we are talking about the step input. Okay. So as the energy absorption will be reduced, what will happen? Rule number 6.
Yes, sir.
As the energy absorption will be reduced in this system, what will happen?
It will come steady state.
Yeah, it will come to steady state. It will become underdamped and it will exhibit. So we are reducing this. See, if we are reducing this, it will allow the system to oscillate also, and while in the transient state, it will allow it to oscillate, and also it will allow it to overshoot. So that will become an underdamped system. So this is very important, that if the energy absorption will be reduced, the system from over damped will become underdamped and it will exhibit overshoot. It will have the oscillations also. I hope this is clear. Any questions regarding this? So next is underdamped response. Now you can see underdamped response. For this response, C of S we have got is 9, it's constant 9, the A value, S square plus 2S plus 9. Sorry, B value is, B is here, A is 2 and B is 9. You can see here. Our general form is B by S square plus AS. So B is 9. A we are changing from, earlier we had 9. Now we have assigned A value as 2. Let's see what is going to happen in this case. Now again we are using the step input. In this case, if we are going to get this S square plus 2S plus 9 is equal to 0, then again we are going to use what we call it uh, quadratic equation, minus 2 plus minus under root of b square minus 4ac, that is 36 divided by 2a, that is 1. So s1 of 2 will become minus 2 plus minus, that will be under root of minus 32, that will be 8 into 4, 2 into 2 is 4, 4 into 2 is 8, is 2, that will be, okay, 4, sorry, 4 and 4 is 16, 16 and 2 will be 32, fine, divided by 2. So we can have s1 of 2 as minus 2 plus minus j, under root of minus 1 will be j. So out of these two, 4 will come out, 2 will 2, and 4 under root of 2 divided by 2. So we will cancel off 2, that will be minus 1 plus minus 2 under root 2. So 2 under root 2, we can write 8, whatever you want to write, it doesn't matter at all. So I'm writing 2 under root 2. But if I want to simplify it, I can write minus 1 plus minus under root of 8. One and the same thing, you can write anything. So now what we have here, we have complex and conjugate roots. So it's very clear now. One, we have step input, one pole will come from the origin. So that will develop, that will produce a constant force response. So again, let us interpret this now. Now here, what is going to happen? The function has a pole at the origin that comes from the unit step that we know. I'm not going to write this. And then we have two complex poles, that one pole, so origin, and two complex poles that will come from the system. That means from the transfer function that comes from the, or that are obtained from the system. So this is the first point. The next point here is, now we have two things. We have two things. Now, the poles that generate the natural response are what? They are these complex poles. Okay, we see that this real part of the pole matches the exponential. So here it is very important. The poles that generate natural response are, I will write that, you already know. There's nothing new in this case. The poles that generate natural response are, what are these poles? These are S is equivalent to minus 1 plus minus under root of 8. These are the poles responsible for generating the natural response. Now it is very important for us here. See, now there are two parts of this pole. This is a complex pole. This is not a simple real pole, negative real axis or positive real axis or origin. This is a complex pole. You have to understand what is the, how the complex pole will uh, how the complex poles have to be interpreting. Now first is, a real part of the pole matches the exponential decay. So this should be very important for you. So real part of the pole that will be responsible of that will be responsible for what? Real part of the pole will be responsible for exponential decay frequency. Yeah, exponential decay generated by the exponential decay, we can write it. So exponential decay that will be generated by the real part of the pole. So here it's very important, the real, I'm repeating again, real part of the pole will be responsible for exponential decay that will be generated by the real part of complex pole pair. So I'm writing in simple words. Now, second is, this is fun. While the imaginary part of the pole that will match the frequency. So imaginary part of the pole will be responsible for sinusoidal oscillations. So imaginary part of the pole, imaginary part of pole, this will be responsible for sinusoidal oscillations. So complex pole will have two parts. Complex pole pair is there. That's a complex and conjugate poles. Complex and conjugate pair of poles is there. So what they have, it have a real part, it will have a second, it will have a imaginary part. The real part will be responsible for exponential decay. So this clearly it will be, there will be an exponential decay in the response. So that it will be responsible for the exponential decay, real part. Imaginary part will be responsible once there is decay, but imaginary part will make sure that there are oscillations or sinusoidal oscillations will take place unless and until those oscillations will die down and they will settle down at some steady state value. So again, I'm telling the general damped sinusoidal response for second order system, the transient response will consist of exponential decay amplitude generated by the exponential decay amplitude generated by the exponent. We can write down to be more precise here, exponential decay amplitude that will be generated by the real part of the system pole, and the sinusoidal waveform or the sinusoidal oscillations, we can use the same word here, sinusoidal waveform or the sinusoidal, sorry, sinusoidal waveform or the sinusoidal oscillations that will be generated by the imaginary part of the system pole. The time constant of the exponential decay will be equal to the reciprocal of the real part. So time constant will be equal to what? Reciprocal of the exponential decay is will be equal to reciprocal of the real part, that we already know, and the value of the imaginary part is the actual frequency of the sinusoidal oscillations. Okay, so this one I want to include one point here, that sinusoidal frequency is given the name damped frequency of oscillations sometimes. This sinusoidal frequency also is given sometimes the name of sinusoidal frequency, is sometimes synonymously used as damped frequency of oscillations. Okay, so finally the steady state response of the unit step was generated by the input pole located at origin. We call this type of response as underdamped. So this response will be called as underdamped response. So let us have a look at the, sorry. Okay, let's have a look at this response now. Just a second, just hanged. Okay, so have a look at this. Now let us say that we are getting a response here. I'm writing. We're not worried about how we are calculating it. We are getting a response like this. See, underdamped is number 2. I will mark this here. These interpretations are very important. So 9, we have used the same thing in all, but we are manipulating just these poles. I have told you pole, by varying these parameters, that means by varying the pole values, we can we can change the response. That was initial my point. That's what I'm trying to authenticate, or I'm trying to validate that point here, that the varying these parameters will change my response. Now I am varying this b parameter here, sorry, a parameter here, that a parameter I'm varying, and I'm getting the different types of response. Now you can see, now let's say the response is equal to 1 minus 1.06 e raised power cos of under root t, this much. I will get this response for you. Now, how it will be? It will be, in this case, what will happen? There will be transient response. It will move like this. And then what will happen? After that, because overdamped had a large amount of energy, it will not have so much of energy, then it will oscillate about the sinusoid, oscillate about the steady state value. So after some oscillations, there will be, after some oscillations, see, it has reached to a peak, there will be overshoot. Now after that, it will come down. This real part will be responsible for the exponential decay, whereas the oscillations, imaginary part will be responsible for the oscillations, and finally they will die down and settle down at the steady state value. So in other words, I will draw a simple graph for you. This graph is very clear. So if I am drawing a graph like this, underdamped is the most important thing out of these. Okay, so what is going to happen here? It's like this. There's a transient response. Okay, fine. Then we will reach a steady peak, overshoot will be there, and then because of the real part, there will be exponential decay. From here it will start the exponential decay. Once the exponential decay will start, it will be accompanied by the oscillations, and those oscillations will die down after some time, and we will reach a steady state value. So this is exactly what is happening in the underdamped response, c of t, and that is a time t here. And I will show it by the another curve. So here, this exponential decay, this decay here, from here. Decay means this, from overshoot, it is going down. The value is going down like this. Now this exponential decay here, so who is responsible? Real part, real pole. Exponential decay will be generated by whom? Exponential decay will be generated by exponential decay will be generated by real part of the complex, by a real part of complex pole pair. So it has to be remembered forever. Now what will happen to this sinusoidal oscillations? These oscillations are there. These oscillations are there. So these oscillations, who is responsible for these type of oscillations? So sinusoidal oscillations will be generated by whom? We also called it sometimes damped oscillations. Sinusoidal oscillations are generated by, these are generated by imaginary part. Imaginary part of the complex pole pair. So these two things are very important, and you should know for each type of response. So this is, I have shown here to be more precise, and this response will be exactly lying like this. Okay, we have conjugate pairs, and each will have its own responsibility. Now let's, I think roll number 6, roll number 10, roll number 8. Is it clear?
Yes, sir.
Clear or not?
Yes, sir. Clear.
Okay, let's move to the next. Okay, next is, now you have to tell me roll number 6 जो मैं पूछूंगा उसका answer you have to answer now that. Next is your undamped. Third case I am taking. Undamped, you have to refer to that figure D. Undamped. Now for that, for this response, what we are doing, sorry, for this response, what the manipulations we are doing like this. 9 is as usual, B, so it's not going to change. S square plus 9. So we are using, this is a step S square. So we are not A, we are using as 0. You can very clearly see here. Now this A we are using as 0, S square plus 9. 1 by S is from the step input. Okay, so that's the response we are getting here. Okay. Now again, function has a pole at origin. I'm going to repeat this. I'm not going to write this here. I will just function has a pole at the origin that will come from what? Unit step input, and two imaginary poles will be there. See, S square plus 9 will be equal to 0. S square will be equal to minus 3. S square will be, sorry, S. So S will be equal to plus minus under root minus 3. So that will be plus minus j under root 3. So these are the roots. Now, again, I am repeat, the function has a pole at the origin, fine, that will come from the unit step input, and two imaginary poles that will come from the system. This is very clear. System poles are transfer function poles. Then input pole at the origin
S3
generates,
आता ना,
yes,
S3 आता ना.
S3.
Okay, डबल अंडर रूट है, ठीक है सर.
I don't understand what you're telling. S minus है ना 3, sorry. Okay, here you're talking about here. Yeah, you are correct, but my answer is still correct. ठीक है, ये 9 आएगा
Yes, sir.
यहाँ पे. Okay, okay, fine. It doesn't matter. I think now it is correct. Minus j, and that will be
तो
3.
सिंपली
Sorry.
3 आएगा ना.
Yeah, yeah. Fine, 3 आएगा, कोई बात नहीं. My mistake, sorry. So that should be plus minus j3. That's correct. You are correct. Okay. Now my aim is different. The input pole at the origin will generate what? The constant force response. I'm not going to write this now. You know this. And two system poles on the imaginary axis at j plus minus 3 generate a sinusoidal natural response. So this we know, plus minus j3, they will be developing sinusoidal natural response. So that you know, I have told you. Okay. Now whose frequency will be equal to pole location of the imaginary pole, that we also know. Now in this case, what will happen? Is there a real part? Row number 6.
No, sir.
Real part is there?
No, sir.
It's not there. So there cannot be. I have told you, real part is responsible for what? Exponential decay. That will not be, exponential decay cannot happen here. So what is the possibility here? Here we have only imaginary poles. So what are the imaginary poles responsible for? Sinusoidal oscillations. So there will be no decay, but there will be sinusoidal oscillations. So this type of response is called undamped response. Why? Because if we have to write without partial fraction, so one will be, that response will be something like k1 plus k4 cos of, so that will be deriving, you don't worry about this. This is the, so in this case, note, we have to note one thing. Absence of real part, please note down these things. I will write down this for you. This is very important here. I will first tell you that the absence of the real part in the pole corresponds, what corresponds to it? It corresponds to an exponential that does not decay. So here exponential that does not, exponential decay will not be there. So that's very important. So imaginary poles will be responsible for the sinusoidal oscillations that will be there. So you can see here very clearly that this type of response is undamped. That means there is no damping at all. Here, clear a sinusoidal wave will be there. See here, it is It is going, rising, going up, transient, rising. There is no exponential decay like this because absence of that real part will not allow any damping, or it will not allow the exponential decay. So I will be writing that point. The absence of a real part in the pole pair corresponds to what? Corresponds means what it says, corresponds to an exponential that does not decay. So there will be no decaying exponential that does not decay. It's very important. Mathematically, e raised power minus 0t will be 0 is, that will be 1. So there will be e raised power, the real part will be exponential decay. This is 0. So that will be equal to 1. So there will be no decaying at all. I hope this is clear. Anybody has a questions? Okay, let's move further. Next is critically damped response. The response number 4 is critically damped response. So for this response, how we are choosing the response. Let's see what changes we are making. For this response, B will be constant as 9. 9 divided by S is from unit step input, S square plus 6x plus 9. So we are using A value, we are choosing here as 6 in order to change the response. So now what we'll be getting? S square plus 6x plus 3 is 0. So we can simply write it, yeah, S plus 3 whole square. That will be S square plus 9. No, okay. Sorry, this is 9 here. This is 9. S square plus 9 plus 6x. So we are getting it. So we can write this response can be written as C of S 9 divided by S plus 3 whole square. Now what we have here, you can see we have one pole at the origin that will develop a constant force response and two repeated real poles. Two repeated S is equal to minus 3. So that will generate a natural response. So I'll repeat it. Function has a pole at the origin that will come from the unit step input, and two multiple real poles that will come from the system. That is clear. Input port at the origin, it's very clear, will develop what? Will generate or develop, whatever you call it, a constant force response. And the two poles on the real axis, they are going to do what? The two poles on the real axis generate a natural response consisting of an exponential and exponential multiplied by time. Now we have imaginary part missing. So one will generate exponential, and another will also generate exponential, but that will be multiplied by the time. So where the exponential frequency is equal to location of the pole, real pole, that we already know. So what will be the response here? Sorry. Okay. What will be the response here? We can expect the response as C of t equal to K1 plus, then the first will be exponential because we have real part now. Second will be that response will be multiplied because the multiple poles are there. Multiple poles. That means same value of the poles. Two we have. More than one means multiple pole. Multiple poles we have on the real axis. Okay. K3t multiplied by e raised power minus 3. So one response will be An exponential, another will be exponential multiplied by the time. Two multiple poles we have. That's why this type of response will be there. So what we are expecting? Roll number 8 is there. रोल नंबर 6 उसका रोल नंबर क्या था जो वो नजदीक ही था 8 था या 10
9.
Yes, sir.
9
Nine.
रोल
Yes,
नंबर
sir.
9 is there.
Yes, sir.
Okay, tell me what type of response we expect now. क्या
Sir,
होगा?
critically damped.
Critically damped means what? It will happen.
सर मतलब मिनिमम एनर्जी लॉस होगी तो ये
That is true. ग्राफ कैसा होगा?
सर
यहीं से समझ आना चाहिए ना आपको ग्राफ कैसा होगा.
यस सर सर
Okay.
एक्सपोनेंशियल राइज होगा और
Okay.
जल्दी पहुंच जाएगा वो स्टेडी स्टेट वैल्यू पे.
Okay, so this will be, there will be transient value and then it will finally settle down. ये होगा. This will be critical value. It will go at 1. No oscillations will be there. Why there will be no oscillations? Roll number 9.
सर क्योंकि इसमें कोई इमेजिनरी पार्ट मत आया ही नहीं.
Imaginary part नहीं है. We don't have imaginary part. We don't expect what? We
Sinusoidal
don't expect the sinusoidal oscillations. So
Yes, sir.
this type of response is called critically damped response. Critically responses are, they are faster. Yeah, they are the fastest response. Please remember it. They are the fastest responses. They will not have any overshoot. So they will not have any sort of overshoot that we have seen in case of underdamped. It has a lot of overshoots and it will have sinusoidal oscillations. So if anybody has a doubt, roll number 9, you have any doubt regarding this explanation?
No, sir. No,
So
sir.
this is, so without actually going into the tedious partial fraction calculations and else also inverse Laplace, we can still ascertain that what type of response we are going to get once we are varying the parameters of the second order system. So that's what initially I have told. Okay, I think this is clear and this you have to remember, not much to remember in this case. So let me derive an expression for the underdamped now, because I have given a response. One of the response I will show you. Rest you can do it yourself. So underdamped, what we had, case number second, I think. I'll be, because that's the most important. Rest are very easy. So case number second. Case number second is underdamped response. Let us derive an expression for that. With this values, okay? With these values I am going to derive just for to show you what is happening. So what was there? We had a step input and then we had a transfer function whose value we have given. This is the like this. So step input is 1 by s. Then we have a transfer function in case of underdamped. Please see it. S square. A we have changed to 2 plus 9. We have got both real and imaginary parts in this case. So this is C of, what is this response? This is for underdamped. Now you can see, we know C of S by R of S is equivalent to G of S, that we already know. So from this we can calculate C of S. What is the inputs? Input R of S is 1 by S. C of S will be equal to 9 divided by S into S square plus 2S plus 9. So this is very clear. From here, 9 S square plus 2S plus 9, okay, will be equal to A by S plus B by, because degree is 2, so we will use BS plus C divided by S square plus 2S plus 9. So multiplying by denominator of the left hand side, 9 will be equal to A into S square plus 2S plus 9 plus BS plus C will be equal to S. So I'm not going to coefficients. I think roll number 9, you can equate the coefficients and get ABC value.
Yes, sir.
I don't have to waste the time because time is not much. So I think you can do those mathematical calculations. So I will get you the value of A will be, I can do it, but it will take some time. B will be minus and C will be minus 2. Please check it yourself. First, you can substitute S is equivalent to 0. You can equate the coefficients and you can get the values. Okay, that's not a problem. Okay, now I want to make this the CS what we will be getting here after substituting these values. It will be 1 by S minus, it will be S plus 2 divided by S square plus 2S plus 9. Now I want to make this, I want to take the roots of this. So how we do this, I hope you remember this, your 8th class. Make the coefficient of S square positive 1, that's positive 1. Take the coefficient of X, half it and square it, half it and square it, add it and subtract it. So S square plus 2S, it will be equal to 1 here. So that will be plus 1 we can make here, plus 9 minus 1. So this we can write as plus 1 whole square. Okay. And this is 9 minus 1 is 8. 8 can be written as under root 8 square. So simple manipulations I will do here. Mathematical manipulations. CS will be 1 by S minus, I can just break it down to S plus 1 because I have S plus 1 in the numerator denominator now, plus 1 divided by S plus 1 whole square plus under root 8 whole square. So this is the scenario. Just mathematical jugglery, nothing else. Why I am doing this? Because I want to use this formula. Laplace of, I'm adding both cos and, please remember your mathematics, e raised power at cos of Wt plus b e raised power minus at sine of Wt. This formula together is equal to a s plus a plus b w or omega, whatever you call it, a square plus omega square. So that means if I am taking the Laplace inverse of this one, I'll be able to get a s plus a plus b omega divided by s plus a whole square plus omega square. Laplace inverse of this will be equal to a e raised power minus at cos of Wt plus b e raised power minus at sine of Wt. Out of this, I am going to get e raised power minus at as common. So I can write a cos Wt plus b sine Wt. Fine for me. I hope this formula is clear. This is a mathematical formula, nothing else. So I will try to use this formula. I will try to get this in terms of this to make this function like this. So I will manipulate the CS according to my formula so that I will get a Laplace inverse of this. C of S is 1 by S minus. So what I am doing, I have A here now, but I don't have A. I will put that A is equivalent to 1, capital A. S plus 1 is fine for me. I don't have any problem because I have here S plus A, here S plus A. So that's not a problem for me. Plus I need B now. B. So B is for me, I need to get this B, which is omega. That means omega is under root 8. So I will write like this. I will write it under root 8 by B is 1. This B, capital B is 1. So this is, you can see, this is A, capital A is 1 here, and capital B, if you take the coefficient of this, is also 1. But I will write this under root 8 by under root 8. I can write it like this. I have no problem in writing this. Divided by, so divided by S plus 1 is fine for me, whole square, plus under root 8 whole square. Okay. So exactly this is formula. A is equal to 1. Okay. Okay. B is equal to also 1. Omega is what? Omega is under root 8. So I'll be using that under root 8, 1 by under root 8 into, okay, sorry, B. I have just, sorry. I should rather like write it this. People may get confused. Yeah, this is, okay, under root 8 into 8. So here omega square omega square instead of that is BW. Omega is under root 8, that is fine. But this B I am writing 1 by under root 8 and I am getting it equal to 1. So exactly I have manipulated this formula and I will get the result on the right hand side now. Sorry. Okay, you can have a look here. So I am just amending the formula. Now I will take the Laplace inverse. Okay, now I am taking the Laplace inverse. So it will be C of t. 1 by s will be 1. That's a unit step. That is 1 minus this formula e raised power minus at. Value of a is 1. So e raised power minus 1t. That is e raised power minus t. And then what we have? A is 1 cos. What is omega? Omega is under root 8 cos under root 8t. Okay. Plus what is b? 1 by under root a. And what is sine under root 8t? So this is the complete formula I am using. Same formula what I have derived above. So after that, let me draw this triangle for you. Famous right angle triangle. Okay, so this will be 90 degree. So I think you remember this sine cos, okay? I don't know how you used to remember. We used to remember Pandit Badri Prasad, Hare Hare Bol. आज जुमा है ये नहीं बोलना है. Okay, 90. So what we have, sine is perpendicular by hypotenuse, okay, and cos is base by hypotenuse. So this base is 1 and this base by hypotenuse, and this what you call perpendicular is 1 by under root 8 we can write here. So we can under root of 1 square plus 1 by under root 8 square. Okay, we can write down like this. Okay, here we have phi. Let us say phi. So what I am going to do, I am going to write sine of phi will be equal to what? It's very clear. Sine of phi will be perpendicular by base. Perpendicular is 1 by 8. Sorry, perpendicular by hypotenuse. Perpendicular is 1 by under root 8. Hypotenuse is what? Under root of 1 square plus 1 by 8 square. Cos is base by hypotenuse. Base is 1 under root of 1 square plus 1 by under root 8 square. So these values I am going to use. Now what I am going to do, I am going to write CFs in order to just simplify the response. 1 minus e raised power minus t. I will multiply this outside. That is under root of 1 square plus 1 by under root 8 square. Okay. Inside what I am going to write cos under root 8 of t, okay, multiplied by cos of phi plus sine under root 8 of t multiplied by sine of phi. You can very clearly see. Outside I am multiplying by this. If you multiply this thing, so you are going to exactly get the same thing. See, this denominator multiplied by the cos will be 1, fine. This denominator multiplied by the sine will be 1 by under root 8. So I am doing just nothing, but I am just making simplifications here. Okay. So C of t will be 1 minus e to power of minus t under root of 9 by 8. So this will be 8. 8 plus 1 will be 9. Under root of 9 by 8, we can write it. So cos A plus cos B plus sin cos A cos B plus sin A sin B will be cos A minus B formula. Cos of under root 8t minus of phi. Okay, so this further can be simplified as 1 minus e raised power minus t. Okay, this will be 3 under root 2 under root 2. 8 can be written as 2 under root 2. And here again cos of under root 8t minus phi. Okay. Now, if we divide sine and cos, sine divided by cos will be tan phi. So sine value is what? Sine value is 1 by under root 8 divided by under root of 1 square plus 1 by under root 8 square. Cos value is 1 by under root of 1 square plus 1 by under root 8 square. Denominator will get cancelled. So we will have the value of 1 by under root 8. Okay. So that means phi will be tan inverse of 1 by under root 8. That will be equal to, if you calculate it in degrees, that will be 19.47. So your response finally will be C of t will be 1 minus e raised power minus t. Okay, and that value, sorry, let me write the value first. That value is 1.06 e raised power minus t, and that is cos of under root 8t minus 19.47 degrees. That's the response you are getting. So that's the response we were getting here. Again, sorry. So you can see here exactly the same response. This is the response we were getting. That's what I have told you. You can derive these responses. This is the response we have shown. Having both exponential as well as two parts, so we can get in underdamped response will be like this. This is a bit of mathematical formulas are there which you have already studied. So you have to go through them again and implement them in this response. So you will be getting this response here like this. Any doubts? Roll number 9, Tanzib.
No, sir.
Yes,
Tanzib,
sir.
ठीक हो? Okay, you can send the log, Tanzib. Okay. So
Okay,
we'll
sir.
continue next time with what second order, some definitions and then derivations. There are 3 to 4 derivations. After that we will be doing the numericals in this case. Okay.
किया मैंने सेंड सर
Okay.